So today, we are doing the fundamental theorem of calculus, part 2, which you will actually be using more often than you will use part 1. Okay. If f is continuous at every point on a closed interval from a to b, and f is any antiderivative of f on the closed interval from a to b, then the integral from a to b of f of x dx is equal to f of b minus f of a. In other words, the integral of a function, a definite integral of a function, is equal to the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. That's what this is. And this is a direct result of part 1 as far as coming up with the proof for it. Okay, this says the definite integral of any continuous function f can be calculated without taking limits. No more Riemann sums, no limits involved. Without calculating Riemann sums, and often without great effort, provided that an antiderivative can be calculated. If you can figure out the antiderivative of a function, this is how you want to solve your functions. The only time you do not use this is A, when you're directed to use another method, which will happen on Monday. We're going to learn another method that does not involve antiderivatives. And I will give you problems that you could solve very easily using antiderivatives, because I'm not going to be mean to you and give you functions you cannot solve with antiderivatives and have you work with something that is very difficult. I'll have you do the problems with something that's easy to work with. But basically, if you can take the antiderivative, this is how you solve the problem. This is how you do the integral. Sometimes you can't take the antiderivative of a function, then you need to come up with other methods. We will have the method by hand. You will be covering that on Monday. But often, if you have your calculator available, you will just use your calculator for it. But if you do not have your calculator available, it's antiderivatives to the rest of it. Okay? And that's what you're doing. It's the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound in any antiderivative. So you don't have to worry about the plus c, because if you put the plus c in here and you have a plus c minus plus c means the constants cancel out. So it's any antiderivative. So you don't have to worry about having that constant thrown in there, because it would cancel itself out when you subtract it from itself. The notation we use when evaluating the integrals is such. You have your integral, which is your normal, the integral from a to b of f of x dx is equal to the antiderivative, big F of x, evaluated from a to b. That's what that little line means. Then you plug in b, then you minus plugging in a. So you find the antiderivative algebraically. This is an algebraic statement. This means we are evaluating it at these 2 points. Others, this is pretty much what I'm going to do is use that. Others, including your textbook, sometimes what they will do is they will put brackets around the antiderivative rather than just the evaluation line at the end. They will often put brackets around the antiderivative and have that be evaluated from a to b. That's the only difference between those two notations, is how do you denote that this is my antiderivative being evaluated from this place to this place. Okay. And that's strictly the notation to do that. Any questions so far? I cannot tell you how important this is from the standpoint of ease of your work. This allows you to evaluate integrals, definite integrals, very, very easily. Okay, if you can do the antiderivative, this is by far and away the easiest thing to do. Okay, it cannot be overemphasized that this is the simplest. And this will give you an exact value. This will not give you an approximation. When you're using Riemann sums, when you're using limits, when you're using any other method, essentially except for this, you are getting an approximation. This gives you an exact value. This is exactly what the integral is. This is exactly what the space underneath the curve is. Not an approximation. When you're using rectangles, you have an approximation. The only thing that makes the rectangle, the approximations better are more rectangles. This gives you an infinite number of rectangles in one swift, easy step. So let's do a couple. Okay, the integral from 1 to 4 of 2x plus 3 dx. This is one where I think the dx is important. I know what I'm going to have to anti-differentiate to be able to do my evaluations. Okay. So here's what you do. You take the antiderivative of 2x plus 3 equals x squared plus 3x from 1 to 4. Plus 3x. Yeah. No, don't need plus c because it says any antiderivative. So I put plus c, plug in 4, I still have blah, 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 plus c. Plug in 1, I have blah, 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 plus c. What is plus c minus plus c? Gone. So your constants disappear. You don't have to worry about doing the plus c when you're using it to evaluate antiderivatives, to evaluate integrals. Okay? When you're doing definite integrals, I should say. We clarify that. We will have times you have to have them, but you won't when you're doing definite integrals. So this is 4 squared plus 3 times 4 minus 1 squared plus 3 times 1. Evaluate the function at 4, evaluate the function at 1. Upper bound minus lower bound. 4 squared is 16. 3 times 4 is 12. 16 plus 12 is 28. 28 minus 1 plus 3 is 4. 28 minus 4 is 24. Easy peasy. If you can do an antiderivative, you can do this. Questions? Okay. Same idea. Example number 2, the integral of sine x minus 2 cosine x dx from 0 to pi. So I do my antiderivative. The antiderivative of the sine of x is negative cosine x. The antiderivative of negative 2 cosine x is negative 2 sine x from 0 to pi. Yeah, the antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. I have that 2 as my constant. This has a constant up front. Equals negative cosine of pi minus 2 sine of pi minus negative cosine of 0 minus 2 sine of 0. Okay, the cosine of pi is negative 1. So negative cosine of pi, so this is 1, minus the sine of pi is 0. So the first parentheses, questions? 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 No. You sure? Okay. No, I don't mind you asking somebody else. I just want to make sure that we were clear before we move forward. Okay. Okay. That's fine. So the cosine of pi is negative 1. Negative 1 is 1. Sine of pi is 0, so it's minus 0. Minus Cosine of 0 is 1, so that's minus 1 for that. And then the sine of 0 is 0. So I get 2. Now, if you're doing a sines and cosines, you got like pi's over 4s and pi's over 3s. So you're going to have root 2 over 3 and root 3 over 3 and that kind of crap. Just leave them in radical form. Don't worry about combining them up into one term unless it's easy to do so. Okay. And this, we want exact values. You do not want decimal approximations with those kinds of things. Okay, ooh, this is the fun one. So, 1, 2, e squared, 3 over r dr. Okay. Well, here's something to make this one easier to do. If you have a constant as part of your integral, you may pull that constant out front. The main reason I'm doing it here is not that the constant is difficult to work with. The main reason I'm doing that here is because it makes it easier to see what the antiderivative is. Not to make it easier to evaluate, but to make it easier to see what the antiderivative is. What is the antiderivative of 1 over r? ln of r. If you have a 3 in there, sometimes it throws people off. So this is equal to 3 times the natural log of r, evaluated from 1 to e squared. So that's 3 times the natural log of e squared minus the natural log of 1. The natural log of e squared is 2. The natural log of e to some power is just that power. The natural log of 1 is what? E to what power gives you 1? 0. You need to have that value memorized. The natural log of 1 is 0. You need to know that and have it memorized. So 2 minus 0 is 2, so this whole thing is 6. If you have the natural log of some number, just leave it as that. Don't worry about making it decimals. Okay. This one's yours.
Would you recommend quarterly?
Okay, let's do this. So I get the integral from -1 to 2 of q squared minus q minus 20 dq, which is q cubed over 3 minus q squared over 2 minus 20q, evaluated from -1 to 2, which is 2 cubed over 3 minus 2 squared over 2 minus 20 times 2 minus -1 cubed over 3 minus -1 squared over 2 minus 20 times -1, which is 8/3 minus 2, what's the 2 there, minus 40 minus -1/3. So then, and then this one's a minus 1/2, and then plus minus 20. So this is that, right? Yep. Yeah. Distribute the negative. Combine up like terms. 8/3 plus 1/3 is 9/3, which is 3, right? So I get 3 here. 3 minus 2 is 1. -39. Negative 59 plus 1/2 is negative 58.5, right? 59.5? No, because it's negative 59 plus positive 1/2 would be negative 58.5 equals negative 58 and 1/2. Now, more than likely, if you had this in your textbook, it would be an improper fraction. AP test would have this as an improper fraction. I'm fine with this at this point. I'm good going back and forth between versions and seeing how. Okay. But would you rather try to come up with rectangles between the two and work that out? No, this will give you an exact answer. That is exact. Anything else you do is actually more tedious than this. This looks like, oh my God, it's a lot of work. This is actually a lot less work than if you broke that down into so many subintervals and you had to come up with the heights for every interval and the area of every rectangle. So you're adding like 8 rectangles together or something else. And we will come up with more complicated on Monday. Okay. And those are still approximations. This is exact. This is an exact value. Okay. And there's a real power to being able to do that. There's a real power to being able to do that.